Okay. So again, we've got this remote island. There are 100,000 immortal, non-reproducing people. Also, nobody leaves, nobody comes in. I didn't state that as part of the condition. So there are always 1,000 people. Okay. Now, half the people are initially sane, but it gets really interesting. Okay. The other half are demented. Okay. Well, there's some fluctuation. It's a very interesting society they have. Okay. Every month, 10% of the sane suddenly turn demented, while 20% of the demented at the same time turn sane. Okay. So I said, yeah, maybe first of the month that happens, and maybe whatever point in the month. Okay. Now what I want to know is how many sane and how many demented do you have at the end, or at the right after the transition in the next month. Okay. Now, people did well on the homework here. And from what I see here, people picked up something about how you set this up with matrices. Okay, I'm going to motivate that and make sure we understand how it all comes about. The first thing we could do, and if I introduce this to people who haven't seen matrices, the first thing they're going to do is they're going to say, well, we got 500 sane people. Okay, 10% of that, that's 50, going to become demented, right? Okay, so then 20% of your 500 demented become sane. So 100 demented become sane. We can even make a little diagram like it. You got 500 sane, 500 demented. 10% of these, or 50 of the same, all this sane here, this demented here, become demented, and 100 of the demented become sane. So after transition, well, you've lost 50 from the sane, you've gained 100 from the demented, so you have 50 more sane people. Is that clear? Okay. And you lost 100, gained 50, so you have a net loss of 50 in the demented, and that gives you this. Okay. And then you can do it again. It's easy to do 10%. You're going to get 55 go this way and 90 go this way. So that's going to give you 595 and 405. Then you could do it again and again and again. Okay. At this stage, it's just an incidental thing. You might look at a graph of the number of sane. Let N be the number of transitions, S be the number of sane. We start at 500. After the first transition, we have 595. After the second transition, we have 550. After the second transition, we have 595. Okay, well, the graph isn't exactly done right. This is a little too high, but you can see that we're going up by 50, then we're going to go up by 45. Okay. So my question is this linear? Well, no, because we went over we have the same run from this point to this point. It's 1 month, right? And from here to here, it's 1 month. But the slope here is 50 plus 50 divided by 1 month, right? Did a fundamental triangle, the run would be 1 month, the rise would be 50. Okay. And then the rise would be 45 and the run would be 1 month. Okay. What kind of function is this? You think that's going to be a quadratic function, an exponential function, or what? Well, in precalculus, we've studied these functions. We maybe can get an answer. Okay. But let's move on a little bit. Instead of doing this again, and again, let's say we want to predict this out to the 10th month. It wouldn't be hard to do that, but it'd be pretty tedious. It would take a while. So we do what we've learned to do. We can say that in each transition, 90% of the sane stays sane, and 20% of the demented becomes sane. So whatever the number of sane and the number of demented happens to be, you're going to use both numbers to figure out how many sane people we have after transition. I'm going to let S and D be the numbers of sane and demented before transition. S prime and D prime. So S prime, D prime. The numbers after transition. You'll agree that S prime is 0.90 S plus 1.20 D. In other words, 90% of your sane stay that way, and 20% of the demented become sane. So the new number of sane 90% of those who were sane stay that way. 20% of those who were demented become sane. Okay. Put it another way. You put that in the form of a matrix product. Okay. Because this tells us the new number of sane. Oh, but getting ahead of myself. You haven't figured out the new number of demented yet. Okay. If I multiply this row by this column, then that product says exactly what we said here. This times this plus this times this equals this. That makes sense? Okay. Similarly, this product will give you the new number of demented. This is just a statement that 10% of your sane become demented, while 80% of your demented stay demented. There's a matrix equation, there you have it. Okay. Now, after another transduction, we're going to use S double prime and D double prime. That should, if the prime is after one transition, two primes is after two transitions, right? That makes sense. Use the same matrix because still, whatever your number sane now is, 90% of them are going to stay sane, 20% of them are going to become demented, and that's going to give you your new number of sane. Okay. I'm not sure I said that right. 90% of your sane stay sane, 20% of your demented become sane. That's what I should have said. That was kind of echoing wrong in my empty head. Okay. Well, that's easy to understand, isn't it? I mean, we understand this and this statement, then it becomes pretty clear. And that's exactly what you did for homework. Everybody got that problem. It was voting blocks. There's only one problem of that nature. So if you actually set up the right matrix and did everything right, that's really good. If you started setting up matrices but got a little confused about where everything goes, that's good. Okay? It's not even fair. It's good. Okay? But we want to nail it. Because we want to understand a fair amount about matrices because they're really important in a lot of areas. Okay? We don't want to beat it to death. And this is the last thing we're going to do with matrices. But here we have it. Okay, well, let's just see how this works. In terms of just S and D, your original number, sane and demented, how do you get this? Well, this is going to be S prime D prime, right? So what I've just written here this is just this. If I want to get S double prime D double prime, what do? I multiply this by this, right? Which means I'm going to multiply this by this. Okay? Because when I multiply this by this, I'm multiplying this by this. What's that going to give me? It's going to give me S double prime D double prime. Okay, take a minute now and multiply this matrix by this matrix. And actually, let me write it again. Since I'm multiplying this matrix by this matrix, I can write that as this matrix squared. Now, that doesn't mean you can square this and square this and square this and square this. That wouldn't work at all. That's not how matrices multiply. You need to write out the two matrices and do rows times columns. So take a minute and see if you can do that. I'm not give you time to do it all, but I want everybody to at least to see if everybody can get a good start on it. Okay, gonna work this out. 0.90, 0.20, 0.10, 0.80 squared. Notice that these columns all add up to 1. 0.90, 0.10 adds up to 1. 0.20, 0.80 adds up to 1. Okay, but I do this. First row times first column gives me okay, this times this times this. Okay. Give myself more room. And if this isn't totally clear to you, well, it's new. So it's this times this, and then first row times second column goes in the first row, second column. That's going to give us times 120 times 0.80. Now, in the second column, I'm not going to write out all the numbers, but I'm going to do 0.10, 0.80 times 0.90, 0.10. This row by this column. It's going to give us 0.09 and 0.08. I didn't write out all the numbers, but if I multiply this row by this column, that's what I'm going to get. And if I multiply this row by this column, I'm going to get 0.02 plus 0.64. Well, if I do all the arithmetic, that's going to give me I wrote down a wrong number here. First row times first column. First number should be 0.90 times 0.90. Got ahead of myself and wrote the 0.90. Just a little there. And that gives us this. And it gives us this. Okay. Well, that is what we get if we square this matrix. Now, there's some really neat stuff we can do. We could square this matrix. This matrix takes us from the start all the way through the end of the second year, right? Or the second transition, second month. Okay. If I multiply by this matrix again, it takes us 2 more months in the future, gives us a 4-month matrix. And if I multiply that by itself, it gives me an 8-month matrix, then a 16-month matrix, and so forth. Now that's really neat. And if we had time, I would love to do that, but we can't. I'm just mentioning it. It's kind of fascinating, kind of interesting the way that works. And we can even come up with sort of a binary number series of matrices, but that would take us a little while. We had 2 weeks to spend on this. We could do some neat stuff. Okay. Now, my point is that we can kind of skip now. You at least understand conceptually that after n transitions, we have S of n, D of n. Like this means S as a function of n. This means D as a function of n. Okay. As n approaches infinity, the nth power of this matrix approaches two-thirds, one-third. That approaches. I'm gonna get covariant and contravariant all mixed up here. Okay, that approaches I didn't complete my matrix over here. It approaches this matrix. Okay. Now you could figure that out if you started calculating by hand. Multiply, square this matrix, you get this. Square this matrix, you'll get a 4-year matrix. Square that, you'll get an 8-year matrix. And already the numbers in your matrix, this number is going to be shrinking down like crazy. And this number is going to approach 0.666666, repeating. And this 0.33333333, repeating. Two-thirds, one-third. You could spend 20 minutes squaring this, squaring that one, and squaring that one, just 3 squares, and convince yourself that this is the case. Now, the theoretical reason for that, we'd have to do eigenvalues and transformations and all kinds of stuff that requires a fair amount of linear algebra, so we're not going to do that. That's kind of what linear algebra does. But it's numerically, you could convince yourself of this. You could even go to Wolfram Alpha and ask it to calculate this to the 100th power. Okay. It's actually fairly easy to do if you transform it using an eigenvector basis, okay? And then transform it back, but you have no idea what that means, okay? And unless you take a linear algebra course, probably never will. So we don't want to say that. There's some powerful mathematics that we can use to prove that this is true. The point is that since you have twice as many sane demented becoming sane as you have sane becoming demented, then these numbers, this number has to end up twice this number in the limit. Okay. And these numbers in the column have to add up to 1. Something's wrong. Okay. I'm writing stuff down without thinking about it. Now I know that the columns have to add up to 1, and they always have to add up to 1. All of a sudden they didn't. And that's because they're right. Okay, now I'm not going to write it out. This is 2/3 S plus 2/3 D. That is what we get if we multiply this row by this column. You can easily verify that. And then I can factor out the 2/3. It's just 2/3 of S plus D. S plus D is 1,000. And this comes out 1/3 of D plus S. Well, D plus S is 1,000. Because S and D are your initial 500 and 500. Even if they aren't 500 and 500, whatever you start with, it's going to end up with this. Okay. Well, that's all we're going to say about it, but I wanted to give you a little more detail on the fact that there's a lot you can do with this. If it's a voting block or if it's stock market, okay, there's a 70% chance that this will go up and a 30% chance that that will go up and all that stuff. You can do models. Now, I wouldn't invest money in the stock market based on a model that you can make, but it gives you an idea of how some of these things are actually done in high finance, for example. The last thing I'll say is S of n is an exponential function. It's a transformed exponential function. D of n is a transformed exponential function. Not hard to figure out what it is, but we're going to kind of stop there. I'll just tell you, that's exponential. So that's a place where exponential functions come to life. And there are many, many models that can be understood in terms of this and the model that you used before. Okay, which is why we have a section here on matrices. Oh, y'all have done really well with it. And we're not going to go into calculating the higher powers, although if you're interested and have time, which you probably don't, you're probably preparing for finals and wrap things up. Be an interesting thing to do. Okay. Okay, so how did we approach this course? First of all, we constructed gold cube shapes. We moved the rectangle, or let's say we just use the words that I should have used. Label the construction lines. We label the construction lines according to the location of the red dot. A little more specific, construct a toolkit function shapes in 4x4 rectangles. Label construction lines according to the location of the red dot. Okay, then represents f of x minus h plus k. The corresponding toolkit functions. Okay. I use the word verify. I'm using too many words because I'm using them too quickly. Don't verify, we validate. Using estimates of f of a and f of x equals c. Now, this f of x equals c is equivalent to the open math notation, the same as the open math notation. It means a solution of the equation f of x equals c. Then calculations. By calculations, we mean we write out what the function f of x minus h plus h is for that toolkit function. And we plug a in and see if we get a number close to the one we estimated. And then we solve the equation using this form and plug in the solution we got and see if it gives us a number close to what we estimated. Okay, that's the whole ball of wax for the first chunk of the course. Okay, and then incidentally, we talk about domains and ranges. Okay, I'm not going to say too much about that right now, but I'll expand on it later. Okay, so then we consider domains and ranges. But one thing I didn't say in here is we can construct tables from our constructed graphs. Okay. Well, that's the same thing as doing this just for a bunch of different points, right? So one thing we do is we make a table of our construction points. Okay, so probably ought to insert that. I should have known that as I was going through. We do a table of construction points. We put that in here. Okay. I'm going to extend this a statement 5. By confirming the table and using estimates of f of a and f of x equals c. Okay. Then we consider domains and ranges. We need to be able to specify domains and ranges based on the graph function. Okay, because the graphs of these functions can almost always be labeled to show the essential characteristics of those functions. Okay. in a 4x4 rectangle, at least for the three functions that we learned to construct in detail. We can pretty much see what we need to see about the function. And of course, we can extend things and so forth. Okay. Now, when I say we construct, everybody needs to know how to do the halving thing, twice as close to this line, twice as close to that line. Okay. Label the construction lines. There we've got a scale. We can fill in more detail to the scale, all that stuff. And I think everybody here pretty much has that down. Everybody who's still coming to class, doing homework. Okay. That's supposed to make these functions very tangible to you. Now, there are the other construction, the other toolkit functions that we can understand based on these instructions. Okay. Okay. You can do composites. I'll give you two functions. You should be able to tell me what the composite is and tell me what the domain and range of the composite is. Some people are a little weak on domains and ranges of composites. So that's kind of involved, okay? It's going to appear on the final. It's not going to be a huge part of the final, but if you're trying to make an A in the course, it's something you probably want to be able to do, okay? And if you can do it, then that's going to be beneficial to you no matter what grade you're trying to make, okay? We can form composites. We can deconstruct a composite function. That means if you're given a function h of x, find an f and g so that h of x is the composite of f and g. Okay. Now that's a little bit challenging. But when you take a calculus course, you're going to be really glad you can do that. Okay. Either applied calculus or a full calculus course. Okay. It's going to make things a whole lot easier for you at a time when you don't really want to be confused about it. Okay. There's reasons for all this. You know, this is a pre-calculus course, trying to give you the knowledge that you need to succeed in a calculus course, be it an applied calculus course or the much more challenging calculus 1, calculus 2 courses and beyond. Okay, so you do composites. Okay, then we do as they calculate the average rate of change of f of x on a given interval a, b. Don't remember how to do that? Well, I don't make sure you do because it's really easy. Okay. Use fundamental triangles. Slopes and rates. And a rate, an average rate of change type rate, is identified with a slope because you do it the same way. Okay. And that leads you to the idea that the derivative of a function at a point is a slope of its graph. And you'll be ready for that. You won't have to puzzle over it and beat your head over it. Okay. Unlike 90% of the people who will be in the class, gives you a big, big head start. And that's especially true of people who put themselves in the class, even though they never even passed Algebra 1. Okay. Actually, you can't put yourself in a calculus class if you never passed calculus. Okay. But some people get through precalculus, remember this stuff for the final, sweep it out of their brain as quick as they can afterwards, and then have to beat their heads against the wall when they're trying to learn calculus or some other topic that's based on understanding of all this. Okay. Now, one thing that's implicit in what we're talking about here, and moving the shapes of graphs around and so forth, is understanding the coordinate plane, understanding what the numbers mean, because my experience is 90% of people come into pre-calculus are very bad at that. They don't really understand. Okay. You give them a rectangle, ask them, what are the coordinates of this left low endpoint, the corner, and coordinates of the right low corner, and they'll list the x coordinates from positive to negative as you go in the positive direction. Put them in the wrong order. I see that all the time. And it comes down to people have used calculators to do it. They've never actually had to think about what to do. Okay. So in this course, one thing I hope you've learned is how to think about what you're doing. And I think you have. Otherwise, you'd run for the hall, run for the woods as early as some people did. Okay. As most people. Okay. So those are kind of basic things about functions. Okay. They're applicable to any function. Now, of course, you're doing an average rate of change. You got to make sure the function is continuous. Okay. That's like, it's not like the reciprocal function, which is here in this quadrant and here in this quadrant and doesn't cross the y-axis. Okay. That's why we emphasize that domain and range, because any rate of change you would calculate between something on this side of the asymptote and something on this side of the asymptote has no meaning. This function has no meaning at the asymptote. To the right, left of the asymptote, at every point it does, but it doesn't at the asymptote. That's a statement worth pondering. Okay. After that, we get into some specific functions, starting with linear functions. Now, this is something that everybody should know coming out of prerequisite courses. But we find it's not so we do have to spend some time on linear functions, which takes time away from the real precalculus. Okay. But linear functions. Okay, you get the intercepts. You got to know that the y-intercept occurs when x equals 0, and the x-intercept occurs when y equals 0. That's not just for linear functions. I could have listed that under some for any function. Okay. Now, of course, some of your toolkit functions don't have necessarily x and y intercepts. Exponential function doesn't have an x-intercept. It approaches the x-axis as an asymptote. It never touches it. You keep moving to the left, you keep dividing the x value by 2. Every unit you move to the left is a toolkit exponential function. You can divide by 2 till the end of time and you'll never get 0. So exponential function has no x-intercept, so you never get a y equals 0 point. If you try to solve for y equals 0 point, you're going to use a logarithmic function. You're going to switch it around and get something that makes no sense. You're going to get the log of 0. Okay. Of course, the reason you can't get the log of 0 is because the exponential function never reaches 0. So it's kind of a circular thing. That's okay. Okay, the point is, not every function has an x-intercept. Okay. Quadratic functions, quadratic functions can be all the way above the x-axis. They never have an x-intercept. Or they could be shaped like this, upside down, and be below the x-axis. It's perfectly possible. Happens all the time. Okay. But if there's an x-intercept, it occurs when y equals 0, and you set the function equal to 0 and see if you get a solution. Quadratic function, if it doesn't equal 0, you're going to get a negative under the square root. Negative discriminant. Okay, stuff like that. But now back to linear functions. This works for all functions in general, not just linear functions, but the first time we really encounter it is when we see it with linear functions. If the function has this form, ax plus by equals 0, well, if you let y equal 0, you get ax equals c, and you solve that for x, you divide both sides by a. You get c over a. Y-intercept when x equals 0 gives you c over b. That leads immediately to your graph, because as soon as you have the intercepts, you can graph the thing. Given 2 points, you can find the function. There's a formula for it, but you ought to be able to do it by substitution. In other words, substitute the x and y coordinates of one point here, then substitute the x and y coordinates of another point. You have 2 simultaneous equations in M and B. And by now, you're really good at solving 2 simultaneous equations. You can do it with matrices, you can do it by elimination, you can do it by substitution. I do observe that people didn't do well with that on the midterm because it was done with linear equations, right? Linear functions. But now that you know it in detail, be sure you can do it with linear functions. Okay, functions. formula, if you want. Y minus Y1 equals M times X minus X1, right? 2-point formula for the slope, point slope formula. Given a point and a slope on the function, okay? That's the Y minus Y1 equals M times X minus X1. But you ought to be able to relate that ideally to the fundamental triangle. Still, I'm not going to ask you to derive it. The best you can do is memorize the formula and apply it. You can survive. Okay, you'd be missing something, but it probably won't hurt you on the final. It probably won't hurt your grade in the course. I say find the point of intersection. You should know that I mean find the point of intersection of two linear functions. But then I wrote out two linear functions. It's abbreviated. It's kind of small, but it should be legible. Okay. And that's just two linear equations you can solve by elimination. Very easy to do. You can solve them sometimes by substitution. If I specify a method, it's almost certainly going to be elimination, because you see now, after we've done the matrices and the simultaneous equations, how elimination works. And you've seen it in augmented matrices, you've seen it in the system of equations. Okay. If I don't specify it, and for two linear functions, one of them's in y equals mx plus b form, and the other's in this form, you might just want to substitute mx plus b for y. It'd be easy enough. Okay. All right. We have applications. To apply linear functions, you're going to have information that allows you to put 2 points on a graph, or tells you a point and a slope. Might be hard to read this word, but it says it'll give you this if you can interpret the information into the coordinate plane. That makes sense? Okay, I've kind of stressed the idea that here's a problem, here's an applied problem. Right there's where it tells you 1 point, right there's where it tells you another point. Or right there's where it tells you the slope, that's the rate. And right there it tells you a point. Just do it, okay? Because you do the same thing with exponential functions. And we haven't really done it with quadratic functions. If you got 3 points on the graph of a quadratic function, you can write 3 simultaneous equations and solve them to find out what the function is. Now we'll talk about, what you do with a quadratic function, what you do with an exponential function next time. Okay, but we'll stop here partly because we're a minute over time. I want to run on time. But there's the beginning of a summary. We'll talk about what we need to know about functions. At least what I'm going to stress about functions. Okay, some of the techniques you got to use and what you got to be able to do with linear functions. Okay, and then next time we'll talk about quadratic functions, polynomials, rational functions. And then once we've got that done, we'll start doing some examples that really flesh out what some of these statements mean. And I'll type out these statements and send you a copy because my handwriting can be maybe a little hard to read. But since I'm kind of reading it to you, you can pick it up off the video and think between the lines of my words. Okay? Okay, well, good luck. Y'all have done real well so far. I hope you do a good job preparing for the final so everybody can make the grades they so richly deserve.